Hey everyone, welcome to This Explainer. Today, we're diving straight into a massive engineering headache we all face: spatial bias in urban environmental monitoring. As modeling engineers and data scientists, we know the standard metrics, well, they just aren't cutting it anymore. So let's look at how we can actually architect a high-fidelity solution. Here's the roadmap. We're going to trace this end-to-end data flows sequentially. We'll start with the resolution deficit and dynamic traffic modeling, then move into emissions and microdispersion, geostatistical fusion, specifically kriging, and finally wrap up with simulation power and the SaaS deployment architecture. All right, section 1, the resolution deficit. Let's look at the actual physical constraints that make standard urban monitoring mathematically insufficient. You know how standard regional models like Copernicus operate on these massive 10 by 10 kilometer grids, right? Well, take a look at the red curve right in the middle of that urban canyon. When you use a grid.huge, or even just sparse physical stations, you're mathematically smoothing out the crucial localized data. I mean, you are completely missing extreme, highly localized pollution events happening right down at the street level. To put a precise metric on this error margin, we are talking about a massive plus 300% magnitude of undetected NOx variance. Think about that. If our baseline misses a 300% spike just because the nearest physical sensor is a kilometer away, our models are basically fundamentally flawed. And this is exactly why we have to engineer virtual sensors down to a 10 by 10 meter resolution. Section 2, dynamic traffic modeling. To actually achieve that 10-meter resolution, we need fundamental mobility data. Let's look at the second layer.
It all starts with ingestion. Here, we're utilizing a deep learning architecture called Traffic Flow Net. It essentially ingests two types of data. First, static GIS descriptors, think road class, lanes, slopes. Second, dynamic telemetry, like floating car data. The neural network takes these input vectors and outputs continuous, baseline 24-hour traffic flow profiles for literally every single segment of the network.
But hey, a predictive model is only as good as its ground truth validation, right? This is our first critical reconciliation step. The neural network predictions are continuously calibrated against actual real-world flow data captured by physical avatar counters. So we aren't just predicting, we are immediately correcting based on empirical telemetry. In our system architecture, we formalize this as the dynamic feedback loop. Moving on to section 3, emissions and microdispersion. Now that we have a perfectly calibrated traffic flow, we need to translate that flow into localized primary pollutants. Notice the vital contrast here. Macroscopic models like Coopert, they basically just give you a homogenized average across a whole road segment. But look at the granular breakdown generated by the Planet-IFPEN engine. By using exact kinematic modeling, specifically calculating instantaneous acceleration and speed at a highly granular level, we can map exactly where emissions peak, segment by microsegment. It's a real game changer. Okay, so next we take those precise, unit-level primary pollutants and inject them straight into the dispersity engine. This essentially acts as a proxy computational fluid dynamics solver. It runs an advanced 2D fluid mechanics simulation to map exactly how those pollutants move through the complex topography of an urban canyon. Methodically, this happens in 3 distinct steps. Number 1, inject those kinematic primary pollutants. Number 2, the engine applies a mathematical finite volume scheme. And number 3, it dynamically integrates localized building heights and real-time meteorology. This optimized numerical resolution gives us a highly accurate, incredibly localized traffic dispersion signal. Section 4, geostatistical fusion, specifically kriging. This is really the mathematical climax of the entire pipeline, where that aerodynamic modeling pays off. We face a massive engineering challenge at this stage, avoiding double counting. See, we have macro-regional backgrounds from Copernicus, which already include generalized traffic noise. Then we have our high-resolution, localized modeled traffic, and our physical ground truth stations. We absolutely have to mathematically isolate these variables before fusing them, so we don't end up counting the same exhaust pipe twice. To solve this, we rely on the Kurrigan equilibrium. Our physics-based dispersity model acts as our spatial prior. Imagine it like a dense mathematical mesh. Then, that mesh is mathematically pulled by the gravitational weight of the highly accurate but sparse physical AASQA stations. We are literally anchoring the fluid dynamics model to absolute ground truth. Section 5, simulation and deterministic power.
Having achieved that equilibrium, let's validate the output accuracy and explore the deterministic capabilities of the pipeline.
Take a close look at the data points for the center and Gerland stations. The orange line is the actual physical measurement, and the blue line is our dispersity output. They are perfectly overlapping. This mathematically proves our pipeline reliably predicts ultra-localized intra-urban peaks right at the street level. We're successfully reconstructing variance even just 100 meters away from a physical reference station. And because all of this is mathematically anchored, it lets us project forward. By modifying the input matrices, say adjusting the EV market share or simulating the implementation of restricted traffic zones, engineers can calculate exact tonnage reductions. We can mathematically validate environmental policy and territorial architecture before a single physical change is made. Now, as engineers, this is a totally crucial technical contrast. Purely correlative statistical models, they're simply extrapolating based on historical patterns. They break down the second the fundamental variables change. But our deterministic physical architecture calculates fundamental physical reality. That is what enables true, rigorous scenario testing. All right, final section, SaaS deployment architecture. Let's step back from the algorithmic level and look at how this whole complex system gets deployed operationally. It's deployed across a 3-layer validated data architecture. Layer 1 handles the complex data ingestion from all those heterogeneous sources. Layer 2 is the hybrid computing core, which runs both our deep learning models and the physical fluid solvers. And finally, Layer 3 handles the complex geostatistical output via kriging. It's a completely automated, reproducible stack. Orchestrated by Apache Airflow, this API exposes a continuous, dense, 10 by 10 meter grid of validated virtual sensors. We have literally mathematically transformed the entire territory into an observable matrix, all available on demand. So I'll leave you with this final thought to chew on. When you transition from sparse, correlative data to millions of deterministic, perfectly calibrated virtual sensors, well, everything changes. How will integrating this level of deterministic, street-level data observability transform the way you architect and engineer your next territorial project? Thanks for exploring this pipeline with me today. Keep building.